Hi, my name is Lowell Wofford. I'm going to be talking to you today a bit about some of the work we've been doing to reimagine the methods we use to manage distributed and clustered systems. I'll also be introducing some of the tooling we've developed for this called Kraken and Layercake. I'm a scientist at Los Alamos National Laboratory's HPC Design Group. I'll be presenting on behalf of myself as well as my two co-authors, Kevin Pelzel and Travis Cotton, who are also part of Lowell HPC. Compute clusters, along with their uses, are becoming more and more ubiquitous. They've long time been the mainstay for high-performance computing, the particular area that I work in, but we're really seeing an uptick and a gain in traction for compute clusters in a lot of other sectors. Examples include VM clusters, or private or public clouds. Container orchestration has given us some wonderful ways to use clusters, things like Kubernetes, OpenShift, Docker, Swarm, but don't necessarily prescribe how to actually build and manage the clusters. We've seen a lot of clusters being built for machine learning, AI, and generally data analytics. And of course, for a long time we've been building clusters of systems to support applications and services, so things ranging from web server farms to API farms to back-end mobile apps, many different things like that. Not only are we seeing more and different uses for clusters, we're also seeing them built out of different things. The hardware landscape is evolving, it's diversifying. We're seeing different kinds of processors, ARM being a new big contender, for instance. Different kinds of baseboard management. We're seeing things like the introduction of Redfish over IPMI. There are different kinds of boot processes. Some of these new systems, especially the less standard ones, sometimes have proprietary methods for booting. Different kinds of networks, many different things like this. Over here to the right, you can see some clippings for three such things that we're dealing with at Los Alamos National Labs. One of them is a bit more future-looking, but two of these I've had to personally deal with quite a bit, and were a lot of the inspiration for some of the ideas and technologies we're going to talk about here. Now, while all of this has been changing, not much has changed for how we manage these systems. And of course, this is not a new idea. There have been a lot of talks on this sort of thing in recent years. But just to sort of recap, the way most cluster management solutions work really hasn't changed in a couple of decades. They all kind of follow the same flow. Somewhere you have a way to define a bunch of nodes for your system. You have some tooling that uses those definitions to build service configs for classical services like DHCP or DNS, that kind of thing. You go restart, or maybe that gets done for you, these monolithic services, and ultimately you hit the power button, whether it's software or hardware, and you sort of cross your fingers and hope for the best. You hope you got everything right, and you spend a good bit of time afterwards making sure everything came up cleanly, doing manual checks on things, and so forth. An alternate version of this might involve even writing images to disk to have a stateful install. But in any case, the basic flow is pretty much the same for most of the existing tools out there. This has done well for us for a long time. You can boot a lot of systems this way. But we can learn from some of the technologies that have evolved outside of this space for dealing with distributed systems, and we'll be proposing that we think there's a better way. We think that we can do better. So I want to imagine a slightly different world for managing these systems, one that follows at a very high level the flow described here. So you'll recognize this to be essentially a DevOps flow, but a DevOps flow that would apply all the way down to the bare metal in the server room. So imagine that you make a config change in Git, and that triggers some automatic tests to run, making sure, for instance, security policies aren't violated, or that basic syntax checks pass, many other things potentially. And if those pass, system images get built. That could take many different forms, but ultimately after that, assuming the images succeed, a set of canary runs are sent out. By canary runs, we mean pick a couple of maybe test pieces of hardware and actually use the images, maybe run some actual higher level tests against those images, make sure that they function. And then this is where things get murky, and this is what we want to talk about here. Imagine this next step that I call the magical mystery management machinery goes and it takes these tested images and automatically starts quickly, reliably, and safely deploying those across thousands or even tens of thousands of nodes in a way that we can really depend on, in a way that we can trust in the kind of DevOps fashion that we're accustomed to in other spaces. This magical mystery management machinery is the question mark black box that we want to explore here. We want to think about what it would take to build something that would fit in this box, that would achieve this task. There are a lot of different ways to talk about the kinds of things you would need to do to fill in this mystery box, this mystery machinery. We're going to take an approach here by looking at 3 different bits of existing technological inspiration for things that might help us build the kind of machinery we would need. Each one will give us a couple of design points that we can use to inspire a little bit later on. Our first point of inspiration is probably no surprise, container orchestration. We've already even talked about it. A container orchestration has shown us a lot of things about how one can use a distributed system effectively, and there's some lessons I think we can extract from container orchestration solutions like Kubernetes for how we can manage the systems themselves. One of the first points here, if we think back to the diagram of how things tend to work today, once we hit the power button, we assume that the job of the cluster management solution is essentially done. One of the things that we can learn from Kubernetes is that there's a lot to be gained from continuously enforcing state. Let's not let our management solution be finished with the power button. Let's let it run continuously and try to keep things in line throughout the life cycle of the system. If anything gets out of line, detect it and try to fix it. For instance, in Kubernetes, if a pod fails, Kubernetes is going to try to restart that pod. We should do similar things when we manage all the way down to the hardware. Another basic thing that we learn, it's one of the most basic reasons that we use containers at all, is that there's a lot of benefit to be gained from abstracting the applications and the services from the underlying hardware. That's really the point of a Linux container anyway, to keep an abstraction layer between the hardware and what we're trying to do with it. Our second point of inspiration here is configuration management. Configuration management, of course, is nothing new, but it does have some interesting things to tell us about how we might want to organize systems like this. The first basic point is that we should centralize system configuration. So in configuration management, for instance, the concept is that the configuration management should be the source of truth for all of the systems that it manages. In general, the principle here is that we should have very clearly delineated sources of truth for our system states. The second point is that there are a lot of advantages to being declarative. That is, say what you want, not how to get it. One of the basic advantages here is that it allows us to abstract how a particular task is done on a system and leave it to the administrator just to say, make this system this kind of thing. I don't care what particular steps you have to follow to get there. Another bonus of being truly declarative is it makes you naturally idempotent. If the system is properly declarative, declaring the same thing twice should just continue whatever it's trying to do already. Our third bit of inspiration is a bit more high level as a design principle, but it's just the concepts of API-driven design. API-driven design tells us to build systems or services in layers, to keep functionality localized to what operates on them and abstract away the details, and then prescribe interactions between these layers. One component shouldn't have to tell another component how to do its job. This allows us to keep things very modular and flexible. For instance, if we've done our job properly, if layer 3 down the road seems like it's too antiquated or has a serious problem, we should be able to throw it away and swap in something completely different that can just speak the same APIs. This is something we should learn from when we think about how to manage large-scale systems going forward. So we can derive a bit of a rough sketch from all of this for the kinds of things we should be looking for. We want to centralize where the state lives. We want to configure systems in a declarative way. We want to continuously enforce states, not just set it and forget it. We want to abstract hardware as much as possible from the ways we use it. We want to clearly delineate layers of functionality. And finally, we want to provide simple APIs to allow components to interact so that as we get sick of one component or another, we can swap it out. So enough of the high-level theory. Let's actually get to the tools themselves and what we've actually developed around these concepts. There are two different tools at play here, Kraken and Layercake. Ultimately, Kraken is a kind of programming framework, whereas Layercake is a particular implementation on top of it that is used for managing clusters and distributed systems. The Kraken Framework is at a high level a framework for building automation tools that have a core set of features that will sound pretty familiar from the list that we just went through. First of all, we want automation tools that are distributed. We don't want to just locally automate. We want to be able to control automation workflows across many, many systems. They should also be scalable. Kraken was specifically designed to scale to the demands of high-performance computing. Kraken is declarative. It operates on the say what, not how principle. Specifically, it's a state engine. So one controls things by declaring a state that is desired, and Kraken knows how to compare that to actual states, and it continually tries to converge them. It's completely modular. In fact, Kraken on its own does nothing. Building a Kraken application is largely a matter of building modules that teach Kraken how to manipulate particular pieces of system state. Kraken is also always on. It expects to be a continually running process on each node participating in the system. Layercake is an application written in Go and is based on the Kraken framework. It's specifically, as I said, an application that is focused on automation tools for provisioning and managing distributed systems and clusters. It inherits all of those basic features from Kraken. It's declarative, it does continuous state enforcement, and it inherits from Kraken's modularity, allowing for different methods, different ways to do things, and the ability to swap them out. It also adds system abstraction in layers, which is the source of the name Layercake. We'll talk about that at some length in a moment. And it, as a side note, is specifically focused, because we're trying to centralize state, on managing stateless nodes. And this has been a technique used in high-performance computing for a long time now. Stateless or diskless nodes have the advantage that you don't tend to get state skew in your nodes versus what they're essentially told to do over time. Again, very popular in high-performance computing, and we're starting to see an uptick in other sectors as well for stateless clusters. So I mentioned that Kraken breaks systems into layers. The layer diagram looks like the one to the right here, more or less. There is a kind of core concept that we want to adhere to here, that changing a higher layer should not require changing a lower layer. This is kind of a principle of least change in the system. So for instance, changing the application running shouldn't require changing the operating system underneath it. That would be layer 2 versus layer 1. Similarly, changing the operating system shouldn't require changing the software control plane. Of course, the software control plane is a somewhat new concept that we're introducing here. We'll talk about it more in a moment. But we can see it as an isolation layer between the provisioning and the hardware and the system images. And finally, these interactions should be modular. We should be able to plug them in and out as much as reasonably possible. So let's go through the layers going down the stack. So the top layer, layer 2, is application and user. This is a very broad layer that we don't actually prescribe in much detail, because it really depends on what you're trying to do. If we're talking about HPC or scientific computing, it's likely that this is the layer at which a user has maybe brought their own container for running their scientific application. Maybe they have a GROMACS container or something like that. But the important thing here is that the system image should have the mechanisms to determine how the layer 2 application is run, but not necessarily what it is. There should be that level of abstraction between them, especially since the particulars really vary pretty dramatically depending on the kind of system we're talking about here. The system images might be many different things as well, but they need to provide the mechanisms to do the necessary things for the next layer up, the application layer. On HPC clusters, a typical thing might be to run a workload manager like Slurm or Sun Grid Engine, something like that. In a different kind of system, this might involve running container orchestration tooling like K3S or something like that, allowing for the layer 2 to be application containers. We want to adhere to a basic principle here, though. We don't want to be picky about what runs in layer 2, and we also don't want to be particularly picky about what image formats are. We should be able to run more or less anything that we know how to attach as a file system, and that has some kind of init process, be it a small application, like a lightweight application container, or a full-blown systemd Red Hat install. Finally, and again, this is kind of one of the more unique features of the way we've designed things here, but it provides a lot of flexibility. We have what we call the minimal OS or software control plane layer, or layer 0. This provides an abstraction layer between system images or personalities and the hardware and provisioning system. The system image shouldn't have to worry as to how it was provisioned. The system image should be able to just assume that it has a certain base level of functionality and continue on. The idea of the layer 0 is to provide that isolation layer. Similarly with the other layers we've looked at, this layer should provide the ability to change out the layer 1 or the system image without actually interacting with the layer below it, which is to say, we want to be able to load a new system image without ever actually rebooting or reprovisioning a system. Finally, provisioning is its own piece in the stack. We didn't give it a layer number. You could call it layer -1 if you wanted to, but we provide as part of Layercake the actual tooling for provisioning. One of the basic principles we operate on is we don't get to dictate the hardware and the firmware, so we need this layer to be as flexible as possible. I'll say as a side note, well, maybe we can dictate the firmware, and that's another talk. Hopefully you can catch Devin Bautista's talk where he will discuss using some of these exact same tools and integrating them in open firmware. Very interesting project. But we try not to make assumptions about how to get to layer 0. The job of the provisioning system is to get us there, whatever hardware that we have, and that might involve having many different paths to reach the layer 0. Let's take a look at what that might specifically look like. At a very high, kind of hand-wavy level, one could think of a standard netboot process as looking something like this little graph here. You go from off to on, you go through some sort of PXE initialization, and ultimately that loads your minimal OS. But different kinds of hardware have different requirements. For instance, we might have a piece of hardware that requires a special BMC config step before we even power it on. We actually have hardware like that sitting around at Los Alamos that you have to sort of jiggle a bit to tell it to initialize in certain ways every time you power it on. So maybe we have to do something like that. Maybe our hardware supports HTTP boot rather than PXE, and so we need to be able to support that as our boot mechanism. Additionally, alluding to the example I just gave, maybe we've got some sort of custom firmware init process, something that does TLS mutual auth involving TPMs or something fancy like that to establish root of trust. Or maybe it just uses a different kind of data store to acquire its images. Whatever the case may be, we want to be able to support that too. And really, all it should take to decide between these things is to have the proper prescription for the node at hand and take the path that you need to get there. So, in this case, extra BMC config step, custom firmware, we should be able to find that path and get there. This is actually pretty much exactly how Kraken as a framework works. I mentioned that building modules was a matter of telling the framework what bits of state you knew how to manipulate. We mean specifically by that things like saying, here's a way to turn a certain kind of system from off to on. Here's a different way. We plug these in, create this kind of graph, and we do graph searches to figure out how to actually manipulate system states. This allows us to keep the provisioning step, and really all of the other steps, extremely modular. We can just plug in more modules that teach us new ways to manipulate state to get to where we need to go, in this particular instance, to the minimal OS. So let's talk a little more concretely about the reference implementation we've put together and we'll be showing you here. I say reference implementation because, as we've just discussed, all of these things can be plugged in and out, but that doesn't mean we don't need to focus on a few particular ways of doing things in order to have a usable tool. So for power control, we've abstracted things through something we call the Power API, which allows us, through different implementations, to control many different kinds of physical and virtual systems. We've also integrated a complete PXE stack inside the binary. All the services required are in the binary. TFTP, HTTP, DHCP are all part of the application. We've also done work on several alternative stacks, non-PXE stacks. We won't really be talking about that here. We've implemented an all Golang minimal OS or software control plane. It's based on the URoot project. If you're not familiar, I encourage you to check it out. It's a non-GNU Go-based userland for Linux. It allows us to produce very, very tiny minimal OS images on the order of about 10 megabytes compressed, and yet powerful. I won't say it's a fully implemented Linux operating system that you might be familiar with, but it's able to do many of the tasks that we need to manage systems. For system image building, we've constructed some tooling. It's actually based around the Builda project, using Docker files and wrapping that with some extra tools to build images and then extract them in a way that we can use them easily. But we can really, as I mentioned before, we can really handle any image format that we can be taught how to attach and run an init process out of. And then finally, we load and attach system images through another API we call the Image API. And there's an accompanying Image API service. That service, currently we're focused on attaching Ceph Rados block devices as our image sources. So that's how we distribute images right now. Again, we can support many different things, but that's where we're focused. It's working pretty well so far. And then we actually load the system images as privileged lightweight containers. Containers is a very overloaded word. We really mean we namespace them a little bit, and that's about it. And then we support everything in these containers, from lightweight microservice containers to full-blown systemd images. For our first demo, we'll demonstrate the basics of how to install, run the Layercake application, and also how to define a state for a node. And we'll go ahead and boot a single node into the minimal OS state. Here on the demo window, you'll see top left corner, this is a serial console to the node we're going to boot. Ultimately, we're going to run Layercake itself in the bottom left. And on the right side, we'll do most of our work through this. Let's go ahead and get started. We install Layercake the same way many Go applications are installed, with the go get command. And then over on the left, you can see some basic arguments, and we run Layercake. At this point, Layercake is running, and we only need to tell it node state definitions. If you take a look at the definition that was just added on the right, this is the definition for our node. It shows some basic configuration type information, and of particular note is the requirement run state sync. This is requesting that the node be in the state that it is synchronizing with its parent. It is how we're going to tell it that we want to have the node booted to the minimal OS. Let's go ahead and do that now. We can inject the state through the RESTful API that Layercake exposes. In this case, we'll use the curl command, though we'll see in a moment that there are cleaner ways to do it. We're now in the process of booting. You can see activity on the left, and we're running at rapid speed here to speed things along. And in just a minute 32 seconds, there we are. We've booted, and you can see that not only have we booted, but we were able to SSH into the minimal OS on that node. We can take a look around that minimal OS a little bit. We can see it's a little bit different than what we're used to, but contains a lot of the commands we might expect. At this point, the node is booted. Now let's see a different way we could have managed things. We have the kraken-ctl command that will interact with through the API for us, so we don't have to run a bunch of nasty-looking curl commands. You can use -h to see what it can do. In the next demo, we'll look at a more real-world scenario. We'll see how we can run Layercake in Kubernetes. We'll introduce the Kraken dashboard, a graphical feedback tool. We'll show how we can use Ansible to generate states. We'll boot an entire 132 node cluster and have the opportunity to demonstrate some of the self-healing capabilities in the process. Let's kick that off. So we can see that we already have Kubernetes running. We were already relying on some of these services, in fact, and now we've created a new deployment for Kubernetes, or for Layercake. We see that this deployment is running, and now we introduce the dashboard. This will give us graphical feedback as things move along. Now let's define some states using Ansible. We have a pre-made playbook here. We're going to run it, and it'll define states for all 132 nodes and immediately inject them directly into the API, and everything gets going. Again, we're running at high speed here to jump through the slow process, but we can see nodes are booting. In general, as they get more green, we're closer to done. And there, we're done. We can see that there are 3 nodes that are having some trouble here. We'll show that we can force one of those to heal. One will heal it on its own, and one of them turns out to actually be failed hardware. We can drill down on one of the nodes and even see the graph and where it got stuck. Now let's look at what's running on a node. We've just SSH'd into the minimal OS on ML001, and we see that it's got a bunch of systemd looking like services running. We in fact can SSH straight to the node. And here we are. We can do a systemctl status and see that systemd is running and is none the wiser that there's a minimal OS underneath it. Now let's try to cycle that errored node there. We just shut it off, and we see that Layercake will immediately try to recover it because it's supposed to be on. We sped that up, but now it's recovered. For our next demo, we'll show how we can build workload management into our system with Slurm. We'll build an image, we'll show how we roll the update, and we'll ultimately run a simple Slurm job. Recall that we're defining our images using Docker files. You can see this over to the left. This Docker file is based on CentOS base, which is what is currently running here. We're simply adding the necessary Slurm bits to this image. We have this script that will build the image. It uses builda under the hood, and also some tools that will help us build a file system and inject it into the RBD store we use to distribute the images. Now our image is done. You can see it's named CentOS-Slurm. And we're going to go use Ansible to tell all of the nodes that they should be running that image. Again, we do this declaratively, and the nodes start doing the right thing almost immediately. Up at the top, you'll see that Slurm starts seeing nodes almost right away, and now, with about 12 seconds gone, all of the nodes are seen by Slurm. The right-hand side shows some still updating. That's just because we use an eventual consistency model. In a few seconds, that would show what Slurm shows. The question, though, is why are there still 5 nodes that haven't rolled? The answer is we've artificially marked them as statefully busy. We'll show how we can see that. We'll clear the state and see that the roll completes. We can use Kraken-CTL to see that. We query the busy states, and we see that, in fact, these 5 nodes are busy. We've just marked them as free, and we'll see that they immediately roll into the cluster. And again, it takes just a moment for the dashboard to see the changes. At this point, we're running Slurm. Let's prove it. Let's allocate a job and run it. We allocate the full cluster here, and we're just going to run srun hostname. This is going to run hostname on every node in the system. And we see it worked like a charm. We're going to do one more quick demo. We've emphasized all along that we think these tools are useful also outside of high-performance computing. We're going to show how we can quickly roll out 4 of these nodes to extend our K3s cluster with 4 worker agents. We look at the RBD store and we'll see that the image already exists. We've pre-created it. It was created in the same way, though. This time, we're actually going to edit the YAML that defines these nodes and add specific configs for just 4 specific nodes. Now we roll it out in the usual way. We see that immediately the nodes start transitioning and they start popping up in K3s node list. And there we are. We have 4 worker nodes, and eventually Slurm sees that they went away. All right, let's recap. We argued that we need better tooling for distributed and cluster systems. We drafted this little flow diagram on the right and identified this gap, this magical mystery management machinery. We derived some guiding principles from inspiration. We talked some theory about Kraken and Layercake, and then we actually played with it a bit. The question remains, Is it the magical mystery management machinery that we need in this diagram? We think we're headed there. It meets the requirements in theory, and it's already very powerful in practice, doing some unique things. It's still got some rough edges. I'm not going to tell you to go deploy your production data center with this today, but we think it's getting there soon. We also hope that we've piqued your interest with what we've shown here, and that you'll join us in getting it the rest of the way. Thanks for listening.